We're going to start this lecture talking about rectifiers, but we're going to use non-ideal diodes, and we're going to talk about power rectifiers as they are passive. Power rectifiers are passive, meaning we don't have to inject power into it. And so we'll start with our... So all of these, I'm going to call this VS. This comes in, and this is our half-wave rectifier. We should be very familiar with this right now. We're going to call this R load, and now we are going to get some voltage drop across that diode. We'll call this V load. And so when we plot this, and we plot VS, if it were a perfect diode, we'd expect there to be a match, but there's not going to be, because we had a 0.7 volt forward bias voltage drop across that diode. We get nothing the other, we get zero the other way. And so this ends up coming in here. Okay? And it looks something about like that. This shouldn't surprise you too much. We've talked about this already. And we can even do a plot like this that shows that VS and then V load, what it looks like, okay, which is it's going to be zeros, and then it's going to take off here at a vertical line here at about 0.7. That's with the 0.7 volt model. So at 0.7, that sucker takes off on a 1-to-1, which means over here at 1.7 volts, this is going to be 0.7 volts. That's how that's going to look. And mathematically, that's how we treat it. Now, the other thing we need to worry about is down here, when the voltage is, when VS is negative, we call this the peak inverse voltage as seen by this diode. In other words, it's reverse bias. The diodes can be maxed out, or there's certain places where they break down. What's the maximum that this sees? In this particular case, it's really simple. It's just VS. It's the absolute value of VS is what the peak inverse voltage that sees. The other thing to note is what this VD here is. And the book gives this as, in this particular case, it's just basically one diode. Okay? It's just, you know, we're just going to say VD. It's just the voltage drop across one diode. Obviously, for other rectifiers, that's going to be different. But these are the two big things to take away, is that our voltage drop, in this case, is going to be 0.7 volts. Peak inverse voltage for this one will be VS. So that's the maximum reverse voltage the diode will see. Because we want to spec the diode for the right purpose. So there's our half-wave rectifier. Okay, what's next? We're going to do the bridge next. Okay? And just so you know, I draw these differently than most books. I do them in a square format that I think is much easier to see. This is our R load plus minus V load. And if you want to draw these and draw them like I do, it's just on the positive side, both diodes are going to be pointed in. On the negative side, both diodes are going to be pointed out. And then you're going to have two opposing diodes tied together on the other side. That's essentially how I do it. And so when we look at this one, when we look at this one as far as what's going on here, if we plot, there's not a lot of room down here. But that's a full, that signal goes like this. So it's kind of what we expected, but there's two things we want to know. First of all, on this bottom side that we have, what's the maximum reverse voltage that's going to see? And so let's just put it through a forward bias case. Okay, so that means VS is positive. We have current flowing through like this, and we can go through and figure out what each voltage is. So the voltage here is going to, let's just say for heck's sake, so that's zero. The voltage here will be VS. This voltage here will be Vs minus Vd. The voltage here will be Vd because it's from 0 up, okay? And we know that these are two forward biased and these are two reverse biased, and so the question is, what does this diode see maximum on the other side? And the answer is Vs minus Vd. The book goes through a lot of math, but I think that's the easiest way to see this. Peak inverse voltage for this one is Vs minus Vd, the diode voltage drop. The other thing to consider about this is what's this here? What's the amount of voltage drop? In this case, we have Vd here, in other words, VL is going to equal Vs minus Vd minus Vd. VL max is equal to Vs minus 2Vd. We have to go through two diodes, so this is going to be a 1.4 volt drop that we have that drops right there. And that's a concern because that means that we're wasting a lot of energy. Imagine that we only have a 5 volt signal going to this, and we essentially waste almost a quarter or a third of our voltage over the diodes. And so that's a significant drawback of this particular setup, of a bridge status setup. The other thing to look at with this is, I'll erase just a little bit down here so that you can see this. Vs to V load, what that looks like. And it looks like this, but these two guys are going to be what I'm going to say 2Vd. Two diode voltage drops before it comes up. And that makes a significant difference. On the half-wave rectifier, those were halved. And so you can see that that's going to be a big change from what we've done otherwise. And the rectifier is going to cause some problems. So there's some drawbacks to this. The drawback to the half-wave rectifier, not this one, but the other one, the half-wave rectifier with just one diode, is that we get half the juice through because we're missing half the cycles. Drawback to this one is that we are losing twice the voltage for the voltage drop over the diodes. And so that brings us to the transformer one. We call this one the full wave rectifier. Okay? And just to keep it simple, what we're going to call this Vs. And I'm just going to draw two transformers on this side and connect them. This can also be a center tap transformer, but the ratio on these is going to be 1. Somebody asked me to put in the dot conventions on all of these. Okay? So these are 1 to 1 to 1 turns ratios, okay? Which means we're going to get a Vs here and a Vs here in that order. And this one was really simple because we come back and that's it. We measure the voltage VL from there to there. And now we have to ask ourselves some questions. Okay, first of all, let's draw. It's going to look a lot like the bridge rectifier, right? Okay, no question there that we get a bridge rectifier thing going on. But the whole trick with this is that we're only going to have to go through one diode at this point. Okay? So, what happens is if Vs is positive, we end up going through this resistor here like this. Okay? And what we end up having is a voltage drop across that. So we get a voltage drop here. We're going to call this effectively 0. This is going to be Vs. And so this drop here is only 1 Vd. That's an advantage over the bridge that we had before. Now, the next trick about this, though, is we want to know what the peak inverse voltage is. So in the same one, this is the diode that was reverse biased. The voltage here is going to be, well, in this particular case, it's going to be Vs The voltage here is going to be Vs minus Vd. That's going to be the voltage right there. The voltage here is going to be minus Vs. So if we look at minus Vs, and so that's going to be another Vs, 2Vs minus Vd is what that one turns out to be. So what that does for us, though, is that means that's a much larger peak inverse voltage. We have to have bigger, more robust diodes in order to withstand that. But everything else is copacetic. Another disadvantage of this one is we do need a transformer. There's no way to do it off of a non-transformer model. You have to have some kind of or center tapped or three taps on your voltage somehow. So we certainly do need that in order for that to work. Most configurations we want that anyways. And in fact, when we teach the 101 class, what ends up happening, we end up using 4 diodes, but we use these 2 diodes to give us a positive voltage. And we use another 2 diodes here to give us a negative voltage for this one. So we end up doing this to give us both positive and negative voltage. You could probably think that in a computer power supply there's both plus and minus 12 volts. So those are our 3 passive rectifiers. All of them have this problem, but there's no way that we can get by that if we want to do power. So power, we're trying to convert one form of energy, typically AC to DC, with all of these. And so what we need to do next is worry about what's going to happen if we really care about that 0.7 volts, as sometimes we do. And this is a little bit down the road, but let's take a look at this. So this is what I call the signal rectifier. Okay? And it is not a power rectifier. It is no longer passive. It's active. We have to inject power. And okay, we have an op amp. This is our V. I'm just going to call this V in. We put a diode here. Our output resistor, this is going to be V out. We always need someplace for the current to go through, otherwise we get out of control. But this, with the effective advantage of this, is it matches because of the op amp. Sorry, that should be a perfect match. So we get a perfect match. But this doesn't transfer power. What does this do? This messes with signals. Okay? And so what we end up having with this particular thing is we want to let's take a look here. So V in, the op amp does all it can to make this V in. So if V in is positive, the diode, this is going to put out a voltage here. It will compensate for it to make this here. And so this will be V in plus 0.7 while it's positive, which makes this V in so that these two match. Remember, on my analogy of a diode, there's a guy in here looking at these 2 inputs, cranking the voltage to make sure that these 2 are the same. That's what he does. When VI is less than 0, when VI gets less than 0, what ends up happening, this can no longer compensate for this. So this goes off the rails. This goes negative voltage, negative rail. Okay? But since that's so negative, and this is 0 over here, and there's no current that's going to flow through the rest of the circuit, this is just going to pull it to 0, and we have 0 during that period. So this is a half wave signal. This does not transfer power. Why would we want to do it? We would want to do this if we have a very small signal that we want to rectify. So if we go back to old 80s style equipment and you got out your tape deck, it would have this needle here, and they would have all these marks going around here, and this would say VU. Okay? And this would measure how loud it is. Now, audio sounds typically within the sound system are below a volt. And so with 0.7 volts, the 0.7 volt drop that we have across this is just going to mess stuff up. But we have to get an average absolute amplitude, okay, an absolute average amplitude. And so you'd use something like this, throw it through a capacitor and an RC circuit for low pass to get this to, so this does half-wave rectification perfectly. What if we want to do full-wave rectification? Well, let's talk about the negative first, and all I'm going to do, watch, I just flipped it the opposite way. Now, if VI is positive, no way, no how, this guy is going to be able to change this voltage high enough to overcome this diode. We change this voltage higher, this resistor blocks it from the other side, this becomes an open circuit, and this becomes 0. If VI is negative, at negative, this voltage here turns negative, okay, because it wants to match these two guys, so it puts out a negative voltage. And so then we get a voltage drop from here, 0.7, and we get V out, okay? V out, and this V out here, I've had that wrong before, those two are going to match this one and this one. And so what do we end up with? This one is, well, the negative half, okay? So we get a negative half-wave rectifier. So what we do is we put two of these together. Tie the inputs together. This one has the diode facing the opposite way. Okay? And then we have some sort of resistor to 0. And now what do? Invert one of them and don't invert the other. And I'm going to invert, actually, this is the positive half wave. I'm going to invert this one. Okay? I'm going to invert this one. And there's a reason for that. And then both of these get a resistor out, and we put them into an inverting summer. Okay, so it takes 1, 2, 3, 4 op amps in order to get a full wave signal rectifier. We will build this in lab. Okay, and so we need to know that this kind of stuff exists in there. This is all kind of jumbled at the time, but know that it's going to take the positive half. This is the positive half. We invert it, negative half, and then we put it into an inverting summer to get a full wave rectified signal that matches. And this is not power efficient. This is not meant to be power efficient. This is meant to convert signals, really small signals in this. And so those are different op amps. Let's just do one more thing with these. The nice part about this that we can get is for that half waver, it looks just like this. Okay? For the full wave signal rectifier, it looks like that. They're both, that one looks like a perfect absolute value. And so this leads to a little bit of what analog computing is. And so if you've ever had a concern about that. Anyways, those are all of our rectifiers. The next thing that we have to do with the power rectifiers is we want to smooth them. We want to turn them into some sort of DC voltage. And that's the next step.